Alright, your GE-7 Series Section 13 Systems, Components, Introduction, Diesel Electric Locomotive Analysis, Diesel Engine Power Source for the Power Transmission Conversion, Brake System, Operational Modes, and Support Function System Monitoring and Protection. And that goes into Electrical Basic Propulsion System, Basic Control System, Basic Battery Charging System, CEE, the CAC System, the CMR Wheel Slip Detection Correction System, Dynamic Braking System, Engine System Monitoring Description, and ESM Diagnostic Chart, Equipment Monitoring Circuits and Indicators. This section prevents diesel electric locomotive analysis. Also cover the various electrical system on board of the locomotive, the system of the support of the diesel engine, for the cover of the engine support system section. Section 10. The intent of the section to provide understanding of how the individual item of the equipment contributed to the function of the air and each of the pertinent system. This will aid with the maintenance personnel of the diagnosed malfunction to determine the correct procedure to be followed to resolve the problem. It's intended to be with the conjunction with the troubleshooting section, section 10-12. For the engine supporting system of section 10 and for the applicable the locomotive, the system schematic diagnostic problems when they occur. It should be noted the variation systems exist for the different model of the locomotive and between the railroad customers. Also, given the complexity of the system, liberties have been taken to the method of the presentation, but some of the systems are presented with the block drawing diagrams and some with line diagrams. One of the additional systems, engine system monitoring, is ESM. It is presented as a separate entity in all cases. The diagram, the drawings are intended for the general guidance of personnel. Diesel electric analysis. Diesel electric locomotive analysis. The intent of this section is presented very brief with the functional analysis of diesel electric locomotive section 13.1 that reflects the portion of the locomotive into the 5 basic areas of the major item of the equipment. The pertaining with these areas are covered elsewhere with the composite of the maintenance manual. Diesel engine power source. The diesel electric locomotive utilizes the 8 and 12 and the 16-cylinder 4-stroke diesel engine rated up to 3 to 600 horsepower. The engine's associated systems are shown in Figure 13.2. The power transmission conversion. The power transmission conversion equipment of Figure 13.3 is to generate the force of the coupler with the pulling and the pushing of the train. The mechanical power from the diesel engine is converted with electrical power by a directly coupled the traction alternator with the AC from the alternator rectifier with the 3-phase power rectifier. In D2 to DC, the transmitted with the traction motor, which are the gear with the locomotive, the axle, wheel with the tractor effort to be developed between the wheels of the rail, is transmitted through the locomotive platform to produce the required force at coupler. Alright, you have your diesel electric locomotive service and analysis. The top left section goes to diesel engine power source with the Figure 13.2, power transmission conversion 13.3, the railroad operations. In between the railroad operations, you have your diesel electric locomotive analysis of the braking system 13.4, operating modes and support function 13.5, and system monitoring and protection 13.6. Your braking system. There are 3 braking systems. Figure 13.4 on the locomotive of the 4th system available to the customer operation. Figure 13.2 show the diesel engine power source. The diesel engine power source breaks down into these categories: engine, fuel oil system, cool watering system, lubricating oil system, engine combustion air system, governing system, and the power. And they commit to the power transmission conversion. Figure 13.3. Air brake. The air brake system regulates for the air brake application with the surface emergency and portion of the position with the either brake hand over the air brake system utilized with the following equipment and components. The air compressor regulated with the maintained air pressure within the preset range of the main reservoirs. To the main reservoirs which store the supply of the air feed with the system. Brake 3, the brake valve of the operator position with the applicable over the air brake. 4, the tread brake of the units provided with the friction brake over the wheels. 5, the necessary piping pressure switches and control valve of the controlled braking. Dynamic braking. The dynamic braking system provides for the means of reducing train speed with the converting in air into the heat energy is accomplished operating with the traction motor generators whose output power is dissipated into the resistor graded configuration of the traction motor circuits. For the dynamic braking is controlled by the moving of the throttle handle to the idle position and the brake handle to the setup position. The operate sequence of the interlocking relays and switch contactors with the connect with the traction motor fields and series of the rectified traction alternator output with the connection with the traction motor armatures to the grid resistors. Figure 13.3 shows the power transmission conversion. The power transmission conversion is to the traction alternator, then the AC 3-phase full wire power rectifier to the DC traction motors to gear, axle, and wheels railroad operations. The magnitude of the dynamic braking power control with the setting of the brake of the control pentameter between the minimum and maximum positions used with the brake handle feedback with the braking current reactor is due to the measure of the magnitude of the current with the braking resistor grid. The high train speed with the braking with the current held constant with any setting of the brake handle by comparing the feedback current with the reference value set with the brake handle position. The constant horsepower excitation control circuit is adjusting the traction motor field current with the value needed to produce the required braking current. The train speed is reduced with the required field current increase with the rated field current is reached. The train speed is further reduced. The maximum rated traction motor field current is held at constant, and brake current is reduced linearly with speed. Alright, blended braking with the customer option. Usually you have the high-speed locomotive, you have the passenger for the blending braking, the basically combination of the air and dynamic braking systems. Handbrake. The handbrake is usually primarily for the parking brake and is applied manually. It's a mechanical system. Figure 13.4 shows the braking system. A braking system breaks down into the air brake system, the blending braking customer option, dynamic braking, handbrake on the railroad operations. Operational modes and support functions. These section figure 13.5 show the depiction of the relationship of several operational modes. They are supporting functions. Horizontal line figure 13.5 between the engine start and run and engine stop may be thought with the idle state from which the other modes they may be entered or excited. Motor cutouts is special case of the motoring which may be entered with the engine control switch in the start position. Your engine start run. The function of the engine start run subsystem is to provide with the switch and circuit breaker with the relay, interlock with the need with the configure with the start generator, the preloop pump with the fuel pump with the starting the running of the diesel engine. Motor cutout. The motor cutout operation is optional capability of allowing the motor with one or more traction motors to electrically disconnect with the traction alternator power output. This mode of the operation may be necessary if for some reason a malfunction with the traction motor circuitry prevents the normal motoring operation. 1/6-axle locomotive traction motors are usually cut out in pairs. Self-loaded. The self-load is a mode optional capability allowing testing the locomotive under the load without actually developing tractive effort. In this mode, the grid resistor normally used the dynamic braking or used the load with the traction alternator output with the power of the traction motors and the disconnect with the interlocking provided to prevent the switching in the in and out self-loaded while under power also low in the self-loaded mode. Engine speed with the excitation control continue with the function of the normal monitoring. Monitoring. The function of the monitoring mode for the operation is to provide throttle control, relay, logic, and reference circuit with the need for the control power to operation of the locomotive. Alright, figure 13.5 operational modes and support functions. They have the controls, the engine start run motor cutout, then the self-load customer options, the monitoring, which breaks into the transition control and dynamic braking and the engine stop. All these follow under the engine governor speed control, these CEC, and speed event control and wheel slip control. The throttle handle located in the operator's control counts with the 8 knots setting plus idle and stop, moving the throttle handle with the control of the diesel engine speed with from each of the knot setting set with the current voltage power limit to each of the knot setting that provides the current relay interlocking motor functions. First handle located with the operator's control of the console that has 2-position forward reverse and 2-position control direction travel the locomotive by setting with the reverse switch for the contactors into the forward reverse position. Transition relay transition control. Function of transition control made with the configuration of traction motor from the serial parallel configuration to an L parallel configuration. When the locomotive increases speed above the transition speed point, approximately 2.5 miles per hour, they also change the all parallel configuration from the series parallel configuration when the locomotive decreases speed 2 miles an hour, approximately below the transition speed point. Transition control circuit sends the locomotive speed from the axle mounted alternator, which develops a signal proportional to the locomotive wheel speed. The speed signal compared to the reference speed signal within the speed event panel, and the output of the comparison function that generates the transition control signal for the indicator for the transition action. The reason for having the transition control circuit is because of the very high transaction motor currents are required to initially start with the train moving, conversely with the very high motor voltage is required to operate the train at a higher speed. The motoring operation to cover the train speed is up to approximately 70 miles an hour. In order to reduce the output of the requirement of the traction alternator to practical values of the current voltage, the traction motors are operated within two series, two parallel configurations, 4-axle locomotives, two series, 3 parallel for 6-axle locomotives at low train speed within 4 parallel, 6 parallel, 6-axle locomotives at higher train speeds. Transition control circuit will provide with a mechanism of switching back and forth between the side series parallel configuration of the train speed varies. Dynamic braking mode has been explained in the braking system section operated through the CHEC control system to the magnitude of the braking current with the limit of the current in the field with the traction motor to the rated value. Or engine stop. Engine stop mode consists of the two procedures: shutting down the diesel engine, normal shutdown with emergency shutdown, normal shutdown involved with an orderly shutdown where the throttle handle is moved, the idle load removed, and the operator performed the normal shutdown procedure indicating the push of the engine push button. The emergency shutdown with all engines consists of the generally reverse the emergency condition whether the normal shutdown is not adequate. In this situation, the throttle handle is moved to the stop position to activate the multiple unit 3 train line, deactivate the multiple unit 16 train line. All locomotives that consist of the will respond to these signals in the case of the engine shutdown. Control of the controls shown in figure 13.5 provide the support for the function operational mode. They may have many more controls that support the operation mode. However, the engine control, governor speed with the control in the CHEC speed event control, wheel slipping control may be considered as a major control circuit. Each of these explained in detail elsewhere within this publication. Your system monitoring and protection. The monitor allows the control system within the engine with the group protection are shown in figure 13.6 with the stated before the view of the brief functional analysis. Overall locomotive system monitor protection events. For the more comprehensive explanation of monitors of the engine system, refer to the engine system monitoring section. Figure 13.6 covers the four major categories: monitoring controls and monitors and control that serve the purpose of the warning of the operator, monitors and controls that cause the engine to unload and return to idle speed, and 3 monitors and control that cause the reduction of the excitation and load to meet the unit's capabilities. System derated. 4 monitors and controls that cause the engine to shut down. One additional control of the sanding is included with the figure 13.6, and an indication status light will be lit when the manual sanding is activated by the operator. All these items figure 13.6 are covered in part elsewhere within this publication or detailed within the composite maintenance manual furnished with the locomotive. Or your electrical basic propulsion system. The basic propulsion system, figure 13.7, consists of the diesel engine, traction alternator, power rectifiers, traction motor. Assuming all the control switches are set up correctly, when the operator pushes the engine start push button, figure 13.7, the control of the wheel flow with the battery of the cranking motor to start the diesel engine. After the engine idle speed, before the locomotive is to be operated, the engine control which switch must be moved to the run position to bring the engine up to speed. The locomotive is now ready for the operator to apply the propulsion power by the operating master control. Diesel engine is mechanically coupled to the traction alternator. The traction alternator is rotating through the rotating machine which converts the mechanical energy from the diesel engine into the electrical energy. Electrical energy consists of a 3-phase AC with a rectifier, 3 banks of the power rectifiers, 1 bank of each of the phase. The resultant DC will be applied with the traction motor. The function of the traction motor to convert the DC electric energy into the mechanical power for the driving locomotive wheels. Basic control systems. Or the basic control system figure 13.8 that provided the means for the controlling the propulsion system during the monitoring operation. Should it be noted that the braking system mode is not shown in figure 13.8 that must be covered elsewhere within this publication. Major equipment consists of the master control of the CHEC panel, the exciter, the CMR wheel split detection panel, current measuring reactors, axle alternator, and speed event panel. The master control enabled the operator to initiate the operation of propulsion equipment by operating the throttle handle. Also reverse handle with the throttle handle notch sliding signals are not, then applied with the CHEC panel. The CHEC panel functions with the electronic control center with the control signal with the power requested to analyze the numerous signals of the equipment such as the master control, the CMR wheel slip detection panel, current measuring reactors, and the diesel engine. In addition, with the CHEC panel, receive the transition signal with the transition control circuit. With the circuit that must sense the locomotive speed, with the axle mount with the alternator develops a signal proportional locomotive wheel speed. The speed signal is compared with the reference speed signal within the speed event panel, and the output with the comparison function for the generator. The transition control signal was sent with the CHEC panel to play with the traction motor in either series parallel or parallel configuration. The CHEC panel is utilized the various signals to regulate the propulsion system, obtain the maximum efficiency, and applying the propulsion power to the wheels. This is accomplished basically by supplying regulated variable current to the exciter shunt field, thereby controlling the excitation. Alright, and then we're going to back out of this. Alright, your fuel system monitoring. Okay, your monitoring alarm control system and engine protection goes from battery voltage protection to the battery voltage detection grid overcurrent wiring and warning indicator to the operator. The next five go to, are locomotive overspeed protection, locomotive overspeed detection and correction, engine combustion air and overload condition, air warning, engine air system faulty detection, generator overload detection, engine temperature control warnings, and engine hot oil, water detection, indication equipment and system failure. And that one goes into excitation load and remove the engine speed. Ground fault, main wire system protection, ground relay, de-energized detection, brake line protection, broken in two protection, power control line, open detection, excitation and load, it remove the engine speed into idle. Alright, then you have the, from your monitoring alarm control system, engine crew protection, engine protection from service to operating condition, water, and it goes to the water pressure fault, the detection, lube oil temperature detection, CHE, excitation system malfunction, excitation field fault detection, wheel slip protection, wheel slip detection correction, and system derated when required. Alright, then it goes into the warning alarms control system for the engine crew and protection series, engine fault conditions, crankcase overpressure detection, automatic engine shutdown. Also, you have the monitoring alarm control system, engine crew protection, and sanding capability, automatic and manual sanding. Then you're back with the warning indication operator, the cipher load, remove the engine speed idle, system derated when required, and automatic engine shutdown to the maintenance required. Figure 13.7 of the basic propulsion system. Note the cranking motor consists of the cranking windings located within the exciter of the auxiliary generator, and the windings are connected within series to function as the cranking motor to start with the diesel engine. You have the battery. Then you have your engine start push button, cranking motor, diesel engine, direct drive into the traction alternator, direct drive to the exciter and auxiliary generator, a three-phase AC power rectifier to the traction motors for the trucks, wheels, and rails. Current with the field traction alternator, thus the traction alternator output of the traction motor of the control during the monitoring propulsion transition wheel slips. Your basic battery charging system. The basic battery charging system in figure 13.9 consists of the battery, auxiliary generator, voltage regulator, the battery tube that supply electrical power, diesel engine starting, auxiliary electrical power when the diesel engine shut down. After the batteries has been used to start the diesel engine, the engine traction alternator have been reached. Running speed, the auxiliary generator, which is driven by the gearbox mounted on the traction alternator, will provide battery charging the DC voltage regulator. Alright, figure 13.8. Basic control system. You have your master control and throttle notch signal, the CHECP, which is reacting, starting in the traction motors and trucks. You got the axle alternator speed event panel going to the CHEC panel. Your turbo speed diesel engine going to the CHEC panel with load control signal engine governor. Your diesel engine going to the direct drive traction alternator, the three-phase power rectifier, the traction alternator exciters, excitation current, direct drive, three-phase alternator power rectifiers, current measuring rectifiers, traction motor, and the trucks. From the traction motor current measuring reactors, CMR current signals to the CMR wheel slip detection. Also from the exciter in shunt field current signal, wheel slip signals back to the CHEC panel. Okay, I think that covered it. Alright, figure 13.9 basic battery charging system. Battery goes to the engine starting voltage, diesel engine, direct drive, traction alternator, direct drive. The auxiliary generator, back and battery charging voltage goes from the voltage regulator, the auxiliary generator, and field control current, and the voltage regulator, battery charging voltage. Alright, the voltage regulator control for the output of the auxiliary generator, sensing the generator from the output of the adjusting field current of the generator to maintain 74 volt DC under the various conditions of the load and diesel engine RPM. With the 74 volt is then supplied with the battery as the charging voltage. The constant horsepower excitation control system is method of the electronic control traction accelerators alternator excitation. The FL138 excitation panel is a major component of the constant horsepower excitation control system. The system referred to as the constant horsepower excitation control panel. Panel contains the 10 plug-in cards, 9 contains electrical components primarily related to the specific control constant horsepower excitation control function. The 10th card is the test card, which contains no electrical apparatus, but will be removed, which, when removed, allows the test kit, check it to be inserted with the test of the constant horsepower excitation control system. Alright, simplified drawing with a constant horsepower excitation control panel, input and output feedback and signals are shown in figure 1310 with a simplified constant horsepower excitation control system block diagram shown in figure 1311. Various signals are fed into the constant horsepower excitation control panel. For example, the turbo speed bridge generator of the turning of the turbo rotor is charged with the constant horsepower excitation control panel to limit the rate of the amount of the engine load, to minimize the amount of the acceleration smoke, and provide simple and reliable altitude compensation over speed protection for the turbocharger. Load control signal, sometimes referred to the reference voltage supply signal, fell to the engine governor to the constant horsepower excitation control panel. Third step, the controlling locomotive performance for each trial notch and reference voltage may be established isolated from the battery so that any charge of the battery voltage will not affect the reference voltage signal, and the notch and control signal of the master controller fed to the constant horsepower and excitation control panel of the train line circuit with the three main reference voltage signals are established for each notch: current limit, power limit, and voltage limit. Figure 1310 shows the constant horsepower excitation control panel input, output, and feedback. You have your input signals going from the engine governor, throttle handle, multiple unit lines, dynamic braking control, turbo speed signals, wheel slip indication, wheel slip signal, transition control, locomotive battery, and the control constant horsepower excitation control puts out the output signals of the exciter, shunt field control, feedback signals, system voltage, system current, and braking current. The system horsepower excitation control panel, the test card 1, field control card 2, modulator card 3, multiplier card 4, turbo speed card 5, comparatory card 6, filter card 7, 8, oscillator card 9, regulator card 10, reference card. Alright, the three-phase output of the traction alternator feeds the full wave of the rectifier bridge of the rectification result in the DC output supplied with the traction motor circuit with the DC with the traction motors path through the alternator current control reactor, or ACCR, figure 1312, to provide the isolated low voltage current proportional system current. The system current signal is fed to the constant horsepower excitation panel. Constant horsepower excitation control panel with proportional voltage developed, and one of the signals required to control the system current and the power of the DC output of the power rectifier is also fed through the voltage control regulator, voltage control reactor. To provide an isolated low voltage proportional to the system voltage to the constant horsepower excitation panel. Constant horsepower excitation control panel, the signal you with the constant horsepower excitation control panel, multiplier circuit the voltage control. The second use of the voltage control reactor signal is to initiate protective action by overriding the braking current control reactor signal if the alternator voltage should rise above normal value. The dynamic braking control signal of the master controller is fed with the constant horsepower excitation control panel of the V of the train circuit with the braking grid current signal of the basic, the braking current control reactor as fed into the constant horsepower excitation control panel. The braking current control reactor provides signal proportional current flow for the armature braking grid circuit with the one traction motor armature. The braking current contact control reactor signal is one of the three feedback signals during dynamic braking. Their other two are the alternator current control reactor and the voltage current reactor. The traction motors field windings are also connected in the series. They're fed with the rectified of the current with the alternator. The current again is measured with the alternator current control reactor. During the dynamic braking, just as it did during the motor power operation, the voltage control reactor remains connected during the dynamic braking, but is since rectified voltage applied with the traction motor field circuit with the load, but the voltage control reactor signal is too weak to be functional. However, the traction motor field current should become an open circuit with the voltage control reactor will become into control with the traction alternator voltage to provide protective function. Constant horsepower excitation panel receive the turbo signal system current signal of the dynamic braking signal, etc. After considering all the circumstances, it can adjust the amount of the current supplied with the shunt field over the exciter. There's amount of the traction alternator gearbox used with the current alternator field current, thus controlling the exciter maximum efficiency obtained with applying the diesel engine output during the drive of the locomotive traction motors. Figure 1311 shows a simplified constant horsepower excitation control system block diagram. The constant we'll start at the mechanical linkage, the RPM, the engine governor, fuel injection, diesel engine, turbo rated, traction motor, alternator, does the load control circuit and load control signal and turbo speed signal to the constant horsepower electrical panel. Also, that it has three from the traction alternator, three-phase AC with the power rectifiers with a DC system voltage system current, to the dynamic braking current with a wheel slip signal from the traction motors train load, the current horsepower excitation control panel. Also on the outside line, there's an axle alternator transition control, the constant control horsepower panel with exciter, shunt field control, back to the indirect feedback to the traction alternator. From your engine governor, then you have the multiple unit lines with the throttle hand position and the dynamic braking control train line put in the notching control system signal, and the dynamic braking field grid current goes in the constant horsepower and excitation control panel. And from the controller of the train line input to the multiple units, the engine speed command goes in the engine governor, fuel injection, diesel engine, RPMs, turbo rater, or mechanical link. Alright, the continued horsepower excitation panel with control panel receive the turbo speed signal to the system with the signal, dynamic braking signal, etc. After consideration of all circumstances, can sense and adjust the amount of the current supply with the shunt field of the exciter's amount of the traction alternator gearbox used for the control of the alternator field current, thus controlling the exciter maximum efficiency is obtained to applying the diesel engine output with the drive of the locomotive traction motor. The CMR wheel slip detection correction system. The function of the wheel slip correction is detect the corrective for slip, wheel slip for the both monitoring and dynamic braking modes of operation. When the wheel slip is detected, measure for the current leads for the traction motor, affecting difference of level of the rate, indicating the wheel slip occurring. When the wheel slip is detected, the excitation is reduced through the constant horsepower excitation control circuits to reduce the power of the traction motor. Also, the wheel slip is also energized to provide automatic standing to opening of the exciter shunt field circuits. A wheel slip with warning light to operator with the control can also will be indicate that the wheel slipping occurs. The function of the CMR wheel slip detection correction system, the figure 1313 is to provide the best possible adhesion traction to protect the traction equipment. The wheel slip circuit detect for the correction of the following anomalies during the monitoring: correct for the wheel slipping, opening, improper motor connection, load axle slip pinions during dynamic braking, and corrects for the wheel slip and open brake circuit. The three types of correction of the wheel slip are provided: one short, sudden wheel slip, one or more lasting severe wheel slips, and third, one to guard against overspeed and simultaneously slip. Alright, then we're going to back out this. I think we're going to go with 75%. This is figure 1313, constant horsepower engine control system block diagram. You have the dynamic braking on the dynamic braking pot, the throttle handle, the speed control relays, governor speed solenoids. Then you have the engine governor, fuel injection, diesel engine, and turbo rotor. The diesel engine goes in the RPMs, engine governor, the reference valve voltage, which is followed back in the summing of the compartment circuits. Also from the turbo rotor diesel engine, you have the direct couple, the 36 alternator, direct couple, the exciter shunt field. Multiple unit lines going to the notching relays, reference voltage, the dynamic braking field current references to the summing of the compartment compare circuits, which then moves into the arrow signal of to the modulator, the solitude generated modulator excitation shunt field driver, and runs on the exciter field control circuit. Also, the exciter shunt field driver that goes to a fault detector, producing excitation and limited power. Your modulator from the exciter field current, the exciter field feedback goes to stabilizer circuit and modulator once again. You have a power match circuit with axle alternator speed detector transition, runs on two parallel with the wheel slip panel and the summing of the compartment circuit on the power reduction system. Power match circuit, which from the speed detector transition axle alternators to the summing on this compartment circuit. What else did we miss? Okay, we're on the multiple lines, notching relays, reference for voltage. The turbo rotor goes to the turbo speed signal, sensor to turbo speed signal, turbo speed converter to the reference voltage, which goes in summing of the compartment circuits on the multiple unit lines. Your rectifier, your power from the alternator, you have the three-phase power rectifiers, a voltage current regulator, alternator current control rectifier. Turn to a transition motor, contactor traction motors, CMRs, wheel slip panel, traction motors, dynamic braking grid, CMRs, and braking current control rigging and the dynamic braking. From the power rectifier, the voltage control rectifier, and alternating current rectifier, you have rectifiers and filters going into two multiplier and multiplier, which goes in system voltage power reduction, and system current to the swimming compartment circuit within the power match circuit. Okay, I think that explains that. Alright, we have the figure 1313 show the traction alternator with the current transformer going into three different, from the top, current measuring reactor number 1 and 4, transformers number 1 and 4, rectifiers number 1 and 4, and then in the center you have the current measuring rectifiers number 2 and 3, transformers number 2 and 3, bridge rectifiers number 2 and 3. And they go. They also have these four transformers between the rectifiers go to a summing rectifier circuit with sensitivity adjustment circuit leverage through all the motors, the traction circuit compartment, also to the compartment and driver, which goes to see control constant horsepower excitation control compartment, corrective action, automatic standing control of the compartment. Your flow response path. Also, your bridge rectifiers go to a voltage comparison bridge through the rate detection circuit, which goes to comparator and driver, level detection circuit comparator, and the comparator circuit goes to the relay drive and wheel slip relay, which was started by the tach sensor on one axle alternator, speed sensing circuit, overspeed detector, relay driver, and wheel slip relay. And then the goes to open exciter shunt field circuit, automatic standing power, wheel slip relay, and additional corrective action. Okay, let's see if we can go with 100. This is the figure 1314 dynamic braking system block diagram and events. Alright, you have a throttle number idle, the dropout alternator field current with the dropout transition relay, dropout alternator field auxiliary relay to the dropout alternator field auxiliary relay, disables exciting shunt field, the dropout alternator field contactor dropout braking switch, and then it goes, it also has the wait for 10 seconds, disable MTA series with a power contactor, disable the series with the power contactors, open alternator field. While waiting for 10 seconds, you have to the spark switching relay, brake handle setup, pick up braking switch. Pick up braking switch goes into disabled reduced exciter circuits, wheel slip overspray circuit, disables the parallel contact monitoring path, disable the parallel contactor monitoring path, contactor traction motor, field log, and traction motor 2 and 3 armatures to grids. From the pickup of the braking switch, you also have to go. It also goes to enabling the alternator field braking, which goes into braking handling and braking, which splits in 4 different ways. To apply the 74 volt, I believe it's 74 volts of braking control, pick up the alternator field, the current alternator field auxiliary relay, and pick up the relay braking relay. Alright, from the top one, the applying 74 volts of the braking control goes to the brake handle between the minimum and maximum value, which was in the control control CHEC panel, generator field current low voltage reference, and generator field current limited reference, which goes into the control exciter field shunt with SAS 1 off spin of a CMR whips wheel slip panel. From the from the CHEC panel, the driver traction alternators field watch exciter output, rectifier 333 bypass output from the traction alternator drive traction motors dissipates into the grid sectors, and braking control reactor goes back into the generator grid current limitations, and the alternator control reactor goes back in the CHEC panel. Now back to the pickup alternator field contactor, pickup field with series of the contactors, pickup motor series of the power contactors, dropout dynamic braking switch relay, and the energizing alternator field relay. Alternator field auxiliary relay goes to the enabled exciter field shunt field, And picking up the brake relay, drops out the engine running relay. Alright, we're going to cut the tape, and we'll come back. Let's see, we're running about 30 minutes here. Alright, I'm going to cut the tape there, and we'll come back for the rest of section 8.